and welcome to part 3 of our Bernoulli trials video series. This is questions that are looking for exactly or experiments to happen. So let's take a look at a couple of examples here. So example 1, a fair six-sided die is rolled until 7 sixes appear. What is the probability that this will take exactly 10 rolls? So this is the type of question that kind of takes the Bernoulli trials a step further. So if we want this to happen or to take exactly 10 rolls, that means we're going to have a 6 on the 10th roll. So I'm going to say the 10th roll is a 6. Now the probability of that, of getting a 6 on that roll, is 1/6. Okay, that's the probability of getting a 6 on that roll, regardless of what has happened before that. Now, in order for the rest of this to be true, we need to get 6 sixes in the previous 9 rolls, and it doesn't matter what order they come in. So in the previous 9, we need 6 out of 9. So we need 6 out of 9 to happen, and we're going to multiply that by this 1/6 here. Now 6 out of 9, that's just going to be a Bernoulli trials using our formula that we're used to using. Again, if you don't want to use the formula, you don't have to. That's the formula there. N choose or times p to the power of or times q to the power of n minus or. You don't need to use that. You can do it this way, which builds the formula. So we want 6 sixes out of 9 throws. Okay, so what do we want? We want to get a 6. Now the probability of getting a 6 is 1/6. How many times do we want a 6? We want 6 of them. Now we also want to not get a 6. We want to get something else. The probability of getting something else is 5/6. And how many of these other ones do we want? Well, if we want 6 sixes out of 9, we want 3 of them. And then the question is, how many ways can this happen? Well, it's 9 choose 6. So we multiply that by 9 choose 6, like that. So here's our Bernoulli trial, and here's our 10th roll. So we go to our calculator, and we can do this in one go. So we have 9 choose 6 times 1/6. That's just to the power of 6. And then it's times 5/6. And that's to the power of 3. And then this is going to be multiplied by 1/6 again, and that's equal to 1.7365 by 10 to the minus 4. So that's 0.00017. I'll just take it to 2 significant figures there. So that is 0.017%. the chances of that happening. So if you roll a die 10 times and you get 7 sixes, which are 7th 6 appearing on your 10th roll, the odds of that happening are 0.017. So very, very small, as you can imagine. Another example then of this one, okay, for all the golfers out there. So a golfer has a 5% chance of hitting a hole-in-one on a par 3 hole. How many balls must she hit from the tee in order to ensure that the chances of getting a hole-in-one is at least 90%? Okay, so this is taking it even further again, and this would be kind of at the upper level of what you could be asked when it comes to Bernoulli trials. Okay, so for this we set up an inequality. So the chances of getting a hole-in-one is at least 90%. So that's our inequality straight away. So it's greater than or equal to 0.9. Now, how do we get the probability here? So the probability of getting a hole in one, we're asked here for the chances of getting a hole in one is at least 90%. She could get 2 hole in ones, she could get 3 hole in ones. So we're going to go with at least getting 1 hole in one. So the chances of getting a hole in one is going to be 1 minus the chances of not getting a hole in one. So 1 minus not getting a hole in one, let's just say that. So what's that going to be? So 1 minus, now not getting a hole in one, so that'd be getting 5% chance of the hole in one, so 0.05, and not getting any of them, that's to the power of 0. And then the rest of the time, not getting a hole in one, so 0.95, and we want that as many times as we need, so that would be n times. And then how many ways can this happen? Well, this can only happen one way, it's n choose 0. Okay, so this looks a bit complicated. We have n's in there that we're not used to, but let's see what happens. Well, n choose 0, that's just 1, so we can say that's 1. 0.05 to the power of 0, well, anything to the power of 0 is 1. So the 2 of these we can forget about straight away. So all I have is 1 minus 0.95 is greater than, 95 to the power of n is greater than or equal to 0.9. And now I can work with this, and I can work through the equation here in order to solve for n. So first thing will be to take 1 away from both sides, so I'll have minus 0.95 to the power of n is greater than or equal to 0.9, take away 1 is minus 0.1. I'm going to multiply both sides by minus 1 to get rid of these minus signs. So that would be 0.95 to the power of n. Remember, when I multiply by a negative, I need to change the direction of that sign there. So that's less than or equal to 0.1. Now I want to get this n out of here. So what do? I use logs. So I take the natural log of 0.95 to the power of n is less than or equal to the natural log of 0.1. Now what I can do is, laws of logs say that I can take this n out in front. So it's n log 0.95 is less than or equal to log 0.1. I want to isolate n on its own. So n, now here's the thing. So log of 0.95, let me just show you that on the calculator so you can see. The natural log of 0.95 is equal to a negative number. Okay, so don't worry about what it actually is. It's equal to a negative number. That's what's important. So that means if I divide by this thing here, again, I need to change the direction of the sign. So n is greater than or equal to natural log of 0.1 divided by natural log of 0.95. So n is greater than or equal to this. So let's do that. So it's natural log of 0.1 divided by natural log of 0.95, and that is equal to 44.89. 44.89. So if n is a natural number that's greater than or equal to 44.89, then n is equal to 45. So that means this golfer needs to take at least n equal to 45, or the golfer needs to take 45 shots in order, on this par 3 hole, in order to ensure that the chances of getting a hole in one is at least 90%. So if she takes 45 shots on this particular hole, par 3 hole, then the chances of getting a hole in one is 90%. Okay. Okay, so that's probably one of the hardest questions you'll get on the Leaving Cert when it comes to Bernoulli trials, something along those lines. So if you have any questions, just ask in the comments below. Thanks for watching, and I'll see you next time.